Hi friends, if I have 1, 2, 3 shirts and these 2 pants, in how many ways can I dress up? Or if I give you these 3 letters A, R and T from the Scrabble game, how many possible arrangements can you make from these 3 letters? These arrangements are called permutations, and that's going to be the topic of this video. Permutations is one of my favorite topics in mathematics, and I promise to make it your favorite one too. So let's learn permutations in a fun and practical way. Before we begin, I'd just like to let you know that do check out the full courses on our website and Android app. To make it easy, I'll put the links below. First, let's look at the fundamental principle of counting. We will start with our shirts and pants example. So let's say I have 3 shirts and 2 pants with me. So let me actually try them out and show you all the possible ways that I can dress up. And you tell me which one looks the best on me. Do put it in the comments below. Now, as you can see, there are a total of 6 possibilities here. 6 ways that I can dress up. But you guys are smarter than me. You must be thinking that why did I try out all these shirts and pants? Because we can easily calculate it. For every shirt, there are 2 pants that I can wear. And since there are 3 shirts, so what is the total? It's going to be 2 multiplied by 3. That's 6. Or you can think that for each pant, there are 3 shirts. So you can do 3 times 2. Once again, you get the answer is 6. So there are 6 ways that I can dress up with 3 shirts and 2 pants. This technique, where we are multiplying out the possibilities, is known as the fundamental principle of counting, or you can simply call it the multiplication principle. The multiplication principle states that if an event can occur in m different ways, following which another event can occur in n different ways, then what is the total number of occurrences going to be of the events? It's going to be m multiplied by n. So it's m times n. Now in our shirts and pants example, m equals 3 for the 3 shirts and n we can say is 2 for the 2 pants. So the total there was 3 times 2, which equals 6. Now we can generalize this principle for any finite number of events. For example, for 3 events, the principle is as follows. If an event can occur m different ways, following which another event can occur in n different ways, and following which a third event can occur in p different ways, then what is the total number of occurrences of the events? That's right, it's going to be m multiplied by n multiplied by p here. So m times n times p. Now in addition to our 3 shirts and 2 pants, let's say I have 2 caps. So what are all the possible ways I can wear these things? That's right, you can apply this multiplication principle because it's going to be 3 times 2, which is equal to 12, because there are 3 shirts, 2 pants and 2 caps. So if you multiply them out, you're going to get a total of 12 possibilities. Now let's look at another example. Let's say in a class there are 24 boys and 16 girls, and the teacher wants to select one boy or one girl to be the monitor of the class. In how many ways can the selection be made? Will it be 24 multiplied by 16? The answer is no. Here the teacher wants to select only one student. So either a boy or a girl. So both the events cannot happen together here. It's either a boy or a girl. So the number of ways of selecting one boy or one girl is going to be 24 plus 16, which is equal to 40, which is the number of students in the class here, right? So when you add things, this is called the fundamental principle of addition. And it states that if there are 2 events which can happen independently in m and n ways, then one of the event can happen in m plus n ways. So see, you're doing an addition here, m plus n. Now let's say the teacher wants to select 2 monitors, one boy and one girl. Then how many total number of possibilities are there? Now it's going to be 24 multiplied by 16. Here we will apply the multiplication principle because you are selecting one boy and one girl. So the total number of possibilities here are 24 multiplied by 16. So be careful guys, and please check whether you need to do a multiplication or an addition. Always read the question carefully and analyze it. Now are you ready to play some Scrabble with me? If we take this 4-letter word like rose, R-O-S-E, how many arrangements can you make from it? Now to visualize that, let's imagine we have these 4 empty boxes here. 1, 2, 3, 4. And I need to fill them with these 4 letters. So let's start with the first box. How many possible choices do I have here for the first box? That's right, 4 choices, right? Because I can put any of these 4 letters like R or O or S or E. Any of these 4 choices can go. So let's say I put the letter R over here. Now for our second box, how many choices do we have? See, we've already filled in the first box with 1 letter, let's say R. So now I have 3 letters here remaining. So I can put any of these 3 letters, right? For example, I can put O, E, S. Let's say I put E over here. Any random letter, right? So there we have filled in the first 2 boxes. Now for the third box, how many choices I have? That's right, we have 2 choices left. So let's say I can put S over here. And for this final 4th box, how many choices do I have? Only 1 choice is remaining. So total how many arrangements could I make? So think again, let me empty the boxes for you. So for the first box, you could choose from 4 possible choices, right? You had 4 possible choices. So this is 4 times, how many choices for the second box? That's right, 3. So 4 times 3 times 2 choices times 1. So total how many arrangements can we get? That's right, 4 times 3 times 2 times 1. So the answer is 24 possible arrangements. And again, note here, we don't care whether the word makes meaning or not. Like for example, réseau may not mean anything. So we are not talking about meaningful English words, any possible arrangements here. And the final answer is 4 times 3 times 2 times 1. The answer is 24 here. Note here that the repetition of the letters was not allowed, since we are given only 1 of each letter. And each of these arrangements is called a permutation. So total of 24 permutations are possible with these 4 letters. Now what will happen if repetition was allowed? So let's say I had more letters here, like more R's and more E's. So all of these were there, like 4 of each you can imagine. And we had more O's and S. So imagine we had 4 of each, right? So now how many possible arrangements are possible over here? So in the first box, how many choices do I have? So let's say I have 4 of each of these letters. So I can put in any of the 4 letters, R, E, S or O. Let's say I put in S over there. So I have 4 choices for my first box. For the second box, once again, 4 more choices. You can put any of the 4 letters. So let's say I put in the letter O over here. So 4 times 4 for the first 2 boxes. For the third box, again 4 choices. Let's say enough letters are there. So I can put in R over here. Again, let's say any 4 choices. So maybe you can put R again over here. So you can repeat the letter because repetitions are allowed here. So for each box, you have 4 times 4 times 4 times 4 choices. So total how many permutations are possible? That's right. It's going to be 4 to the power 4, which equals 256 permutations are possible in this case. So when repetitions are allowed, you can see more permutations are possible because for each box we can fill in any of the 4 letters. So the final answer was 4 times 4 times 4 times 4, which equals 256. So see, the answer will be different if repetitions are allowed or they are not allowed. So come on, let's try this question. How many 3-digit even numbers can be formed from the digits 1, 2, 3, 4, 5, 6 if the digits can be repeated? So the best way to solve questions in this chapter is to visualize them. And for this, since they've given you 3-digit number, you should draw out the 3 boxes. Okay, so let's draw these 3 digits. Let's represent this by the 3 boxes, like this is basically the hundreds digit, the tens digit, and the units digit. So I like to call this the box method, and box method is very often used in this chapter. So now what is your goal? You need to fill in these 6 digits into these boxes, and they're telling you that the digits can be repeated. But they've given one condition, that the numbers should be even. So what does that mean? In the units digit, I can only fill in 2, 4 or 6, right? Because if you put 1, 3, 5, it will become an odd number. So for even numbers, it has to end with 2, 4 or 6. Now what about the tens digit? Here we can fill in any of these digits. So from 1 to 6. So we can put 1, 2, 3 and so on till 6. Same for the hundreds digit. You can fill in any of these 6 digits that they've given you. 1, 2, 3, 4, 5, 6. And see, the digits can be repeated. So they don't have to be unique over here. So total, how many such possibilities are there? How many 3-digit numbers can be formed? So here we are going to use our multiplication principle, right? The principle of counting. So what will it be? So in the hundreds box, I can fill in any of these 6 digits. So it's going to be 6 multiplied by, in the tens digit, there are again 6 possibilities. So multiplied by 6. And in the units digit, don't put 6 over there. It is just these 3 possibilities, right? 1, 2, 3. So we'll put 3 over here. So if you go ahead and multiply these numbers, what will you get? You will see the final answer is 36 times 3, which is 108 numbers. So this is our final answer over here. 108 such 3-digit even numbers can be formed. Now let's try this interesting question based on flags. So it says find the number of different signals that can be generated by arranging at least 2 flags in order, one below the other, on a vertical staff. Vertical staff means basically your pole on which you put the flag, and if 5 different flags are available. So note the question carefully. It is saying that 5 different flags are available to you, and you need to make arrangements of at least 2 flags. Now read the English carefully. At least 2 flags means 2 flags, 3 flags, 4 flags or 5 flags, right? It should be basically more than 2 or more than 2. So again, one very important trick, please draw out this stuff and visualize it. So how will our flags look like? So let's say this is your flag staff, or basically the pole. So you can basically put 2 flags like this, or you can have an arrangement where you can put 3 flags. See, and it says one below the other. Okay, and that's our pole basically, putting the head of the pole there. Or you can have an arrangement where you have 4 such flags, because remember we want at least 2. Or you could have an arrangement where you can have 5 flags, because a total of 5 flags have been given to you. So again, this is just a rough drawing. I hope you're understanding what I'm trying to depict here. The 2 flags, so this is basically the 2 flag scenario, 3 flag scenario, 4 flags and 5 flags. Now the question is, how many such possibilities, how many arrangements, how many ways are there of arranging these 5 different flags, right? So we can say that the 5 flags have different colors. So we can say the 5 flags are, you can call them a color A, B, C, D, E. So these are all the different flags that you're having, 5 different flags. So let's start with the first case. When you're arranging 2 flags, how many possibilities are there? So see, let's say we start putting it from the top, or we start counting from the top. So for the top one, I have 5 choices. I have 5, let's say, colors over there available. For the second one, since I've used up 1, how many I have more? 4, that's right. So here I have 5 possibilities and then 4. And by the principle of multiplication, that means how many total possibilities over here? 5 times 4. So 20 possibilities are here with 2 flags. Now what about with 3 flags? So you can put any of the 5 colors here. Now since 1 has been used up, for the next one, any of the remaining 4. Another one used up, so remaining 3. So how many possibilities here? Very good. 5 times 4 times 3. So this answer will be 60. So this equals to 60 here. Now for this one, if you have 4 flags, then 5 for the first one, 4 for the next one, then 3, and then 2 for the last one. Only 2 possibilities are left. So this is going to be 5 times 4 times 3 times 2. So basically the answer is 60 times 2, right? 120 possibilities here. And the last one, where you're trying to arrange all the 5 flags. So 5 possibilities, 4, 3, 2, and then only 1 left. So it's going to be the same answer, 5 times 4 times 3 times 2 times 1. Once again, you can see we have 120 flags. 120 such combinations are possible, arrangements are possible here. So what is the total number of different signals, right? We are calling each of these arrangement a signal. So how many total signals? Very good. Here now you will do an addition, right? Now don't multiply these numbers. It's going to be 20. So the final answer is going to be, the total possibilities are going to be 20 plus 60 plus 120 plus another 120. So go ahead and add this up. This is 240. 240 plus 60 is 300. Plus 20 is 320 is your final answer. 320 different signals are possible when you are putting at least 2 flags. So once again, we use the principle of multiplication in each case and added it up, and this is how we got this answer. Now here's a telephone number question for you. How many 5-digit telephone numbers? So looks like it's those old phone numbers. In the olden days, you had 5 or 6 digit. Nowadays, they're all 9 or 10 digit numbers. So how many 5-digit telephone numbers can be constructed using the digits 0 to 9 if each number starts with 87? So they're telling you this number starting with 87 and no digit appears more than once. That means repetitions are not allowed. So once again, use that box method, because remember, it is all filling up the boxes. So if we represent our 5-digit number as 5 empty boxes here, this box method is super useful. 1, 2, 3, 4, 5. So that is your 5-digit number. Okay, and let me write down here this is box number 1, 2, 3, or we can say digit number 1, 2, 3, 4, and 5. See, I'm using Roman numbers so that it will not confuse it with the normal numbers there, right? And so the numbers are starting with 8, 7. So see, this is fixed, that you have to put an 8 in the first digit and 7 in the second digit. Okay. Now you have your choices of whatever digit you want to put in. So let's start off. So for the third digit, right, the third box, how many possibilities we have? How many choices here? So actually from 0 to 9, there are 10 digits, but 2 have already been used. 8 and 7 have already taken the first 2 places. So how many digits are left? That's right, 10 minus 2, 8 possibilities here. So I can put in 8 different digits here in the third digit. Now what about the fourth digit? If we move on to the fourth digit, see, repetitions are not allowed. So imagine you have used 1 digit here. So you cannot repeat it. That means you have 1 less possibility left. So 7 possibilities over here left, right? Similarly, 6 possibilities will be left for the last digit because 1 has been used up here. So total, how many such arrangement, how many such numbers will be possible? That's right, we'll use the multiplication principle. 8 times 7 times 6. And if you guys multiply this, you will see that there will be 336 telephone numbers. Your final answer is 336. So use this box method and visualize that, okay, how many things I can put in this box, then the next box. And see, once you have put in one box, since it was no repetitions were allowed, you have only less choices left, right? So you have 7 choices, you have 6. You multiply this out and you can easily get the answer. So is this question clear to you? So in our Scrabble game, we looked at the word rose. We had seen this 4-letter word and we had looked at how many possible arrangements, how many possible permutations were there. Remember, it was like filling up the boxes. So once again, rose is a 4-letter word. So it's like filling these 4 boxes. So how many possible permutations will be there? So like we saw, in the first box, you could put any of the 4 letters. In the next box, you have 3 letters left. In the next box, 2 letters left. And in the last box, you have only 1 letter left because here repetitions are not allowed. So the total number of permutations is 4 times 3 times 2 times 1 and the answer was 24. So you can see what is the multiplication we are doing here. 4 times 3 times 2 times 1. Or you can consider this, if you look at the other way, we were basically doing 1 times 2 times 3 times 4, if I write it in reverse order, right? And this has a special notation in mathematics. When you do this type of multiplication starting from 1 to a certain number like 4 here, this is called factorial of this number. This is called 4 factorial, and it is represented by 4 with an exclamation mark. Okay, so this is not an English exclamation mark like, oh my god, what is this? This is the factorial notation. Another notation was also used is, it is also written like this with this kind of an L sign, but nowadays this exclamation has become very popular. So this is the meaning of factorial in mathematics. Like if you keep multiplying a number starting from 1 till that number, that is called 4 factorial. Similarly, 5 factorial will be 1 times 2 times 3 times 4 times 5, and it is written as 5 with an exclamation mark. So this is called factorial. Factorial of 5 is 1 times 2 times 3 times 4 times 5, and you can multiply and see it will work out to be 120. And factorial is very important in this permutation chapter, because you can see that we'll be doing this kind of multiplication rule, and we might be doing this kind of multiplications a lot. So factorial is very important. So let's look at a little more details about factorials. So in general, if we talk about n factorial, what is n factorial? It is 1 times 2 times 3 times 4 all the way up to n. This is n factorial. Or you can write the other way around. You can think n factorial is n times n minus 1 times n minus 2, and you keep on multiplying all the way up to 1. Obviously in multiplication the order doesn't matter, so whatever is convenient for you, you can use that. Now can you guys tell me what is 1 factorial? Simple. 1 factorial means 1 times 1, right? It's simply 1. Now what is 0 factorial? You might be thinking 0 factorial, anything multiplied by 0 is 0. But here this is an important thing. 0 factorial in mathematics is considered as 1. I know it sounds strange. You might be thinking, but hey, 0 times 1, but you're not doing the counting starting from 0. So this is like a special case. Note that 0 factorial is 1. Okay. Now let's look at this example. What is 6 factorial? So what is 6 factorial, guys? So we can say 6 factorial we know is, if I write it in reverse order, it is 6 times 5 times 4 times 3 times 2 times 1. Right? This is 6 factorial. Or you can write 1 times 2 times 3 times 4 times 6. But you'll see why I've written in this reverse order, because if you look at this part after 6, 5 times 4 times 3 times 2 times 1. If you focus on this part, what is this part, guys? That's right, it is nothing but 5 factorial. Can you see? 5 times 4 times 3 times 2 times 1. So basically 6 factorial can be written like this. It is nothing but 6 multiplied by the factorial of the previous number, 5 factorial. Similarly, we can break down 5 factorial as 5 times 4 factorial and so on. Okay. So I can write this formula. Does this make sense? With this example, if you compare n factorial, like 6 factorial, is the number itself n times n minus 1 factorial. And this is very useful kind of concept that you're learning, that it is the current number times the factorial of the previous number. So remember this notation, it will be very useful for you. Now let me ask you a question. Can you find out what is 8 factorial by 6 factorial? So one way of doing this is expanding it out, writing 8 factorial as 8 times 7 times 6 times 4 all the way up to 1. Same way with 6 factorial. But we are going to be a little smart here. We don't want to do so much hard work. So what we can do is we can write 8 factorial is 8 times 7 factorial, right? Divided by 6 factorial. And 7 factorial, I can again do the same thing, is 7 times 6 factorial. So I'll replace 7 factorial as 7 times 6 factorial. And what is the magic here? 6 factorial cancels, because calculating factorials is painful, right? A lot of multiplication, you'll get a big number. But the good part is this all cancelled. So the final answer is simply 8 times 7, which is 56. So this is a nice example where we use this concept. So that's why I wanted to show you that how you can use this n times n minus 1 factorial or n minus 2 factorial to really simplify out your calculations. Let's try another interesting question based on factorials. If I ask you to do 5 factorial minus 4 factorial, well, once again, you can expand it out. You can calculate 5 factorial, you can calculate 4 factorial and subtract. But that will be lengthy and boring, right? So what is the smart thing we can do here? Once again, we can write 5 factorial as 5 times 4 factorial. And this one is minus 4 factorial. So see, things will simplify out a bit here. So we can take 4 factorial in common and it will be 5 minus 1. So the final answer is simply 4 times 4 factorial. So here you might argue that, hey, again I need to multiply this and find out. That's right. But many times, if this is divided by something, it could cancel off. So you can do this kind of smart tricks and use this n times n minus 1 factorial to your advantage. Now let's understand permutations in a general way. So we can say permutations is an arrangement of n given things. So let's say you've been given n objects, right? And these objects could be letters, digits, flags, whatever. And you take them all at a time or you take only r at a time. So either you're taking all the n objects or a subset of that, r of them. Then how many such arrangements or how many such permutations can we have? So let's understand again this general case with a simple example. So let's say we have taken 3 letters, right? A, B and C. Now if I take all these letters together at a time, right? All of them A, B and C, how many such permutations can I make? So that should be simple, because if you consider our box method, that means we basically have to fill up 3 boxes. We have been given 3 letters and we can take these letters, and again we are going to assume that no repetitions are allowed. So how many such permutations will be there? So in the first box I can put any of these 3 letters A, B or C. Now since I've filled in 1, so I can put only 2 in the next box and only 1 is left in the last box. So total I have 6 such permutations. So in this case, this is the case where I'm taking all the objects and using it, right? So it is n objects where all are used at a time. Now let's say I say out of these 3 letters, how many 2-letter words can you make? So this time I'm not asking for 3-letter words, I'm asking for how many 2-letter words can you make. That means you're taking 2 at a time. So in the second case, we are not taking all the letters, we are taking a subset of them, let's say 2 at a time. So how many will it be? Since you want to form 2-letter words, it's like filling in just 2 boxes. So in the first box, how many letters can you put? A, B and C. That means you have 3 possibilities. So 3 options there. And in the second box, since you have used up one of the letters, you have only 2 letters left. So it's going to be 3 times 2. Once again here the answer will be 6. But the important thing is the difference here, right? Here you're taking all the letters at a time. Here you're taking 2 letters at a time. So I hope with this simple example, you're understanding what is the meaning of permutations of taking all your n objects or r at a time, a subset of them. One important thing to keep in mind in permutations is that order is important. What does that mean? So let's say when you're taking all the letters at a time, then ABC is different from ACB, and that is also different from BCA or BAC and so on. So order is important. These are not considered the same. And the same thing when you take 2 letters at a time. So from ABC, if I take 2 letters, AB is considered different as BA. Similarly, here you're taking, let's say, BC and CB, then AC and CA. So see, this is how we are getting all these 6 combinations, right? Redoing the dialogue. So see, this is how we are getting our 6 permutations. But order is important. AB and BA are considered different. BC and CB are considered different in permutations. Same for the 3-letter case, and here you will also have more possibilities. Okay, so remember this important thing, that order definitely matters. Order is important in permutations. So now let's look at the general case of n objects taken r at a time or all together. So as we were discussing, if we want to generalize the permutation of arrangements of the n given things taken r at a time or all together, then what is the calculation going to work out to? How many such permutations will you get? So let's take the case when we are taking all the objects, all the n objects together and finding the permutations. So once again, we'll apply the box technique here. So let's say you have n such boxes. So 1, 2, 3, 4, all the way up to n. So we are having to fill in n such boxes. So how many permutations are possible? So if you start from the first box, there can be n. You can fill in any of the n objects. Now since it is used up, in the next box n minus 1. In the next box n minus 2 possibilities, and every time you keep multiplying, n minus 3 and so on, all the way down to 1, right? Because you have n such boxes, so n times n minus 1 times n minus 2, all the way down to 1. This is the total number of permutations. So this is your number of permutations which are possible. Now let's take the case where we take r objects at a time. So we are not taking all the entire n, we are considering, let's say, r of them. So this time how many boxes we have to fill in? Because you're choosing r objects, that means r boxes, not n boxes, right? So please understand this point. Since you're selecting only r objects, so this time you have to fill in only r boxes. So let's say 1, 2, 3 and so on till r. So how many possibilities this time? So for the first box there are n possibilities. For the next box n minus 1 multiplied by n minus 2. Because see, in the first box you have n possible objects. Next one you have 1 less, n minus 1, then multiplied by n minus 2. And where will you stop? See, because for the first box you put in n. For the second box you subtracted, you didn't do n minus 2, you did n minus 1, right? Next time for the third box you did n minus 2. So 1 less than this, right? Or you added 1 basically to your subtraction. So we can say it is basically till n minus r plus 1. Look at it carefully. So see, for 3 it will be n minus 3 plus 1. That's n minus 2. So we are going all the way up to n minus r plus 1. So this is basically the total number of permutations when are possible when you take them r at a time. So please understand this. This is very important because the n objects, they can be anything. They can be digits, letters, flags, whatever you're considering, and you want to consider their permutations, either taking everything at a time, then you apply this formula. But let's say if you take a subset of them, right? Then you will be applying, you'll be using this logic and you will get the number of permutations. And once again in permutations, remember, order is important. So ABC is different from ACB, AB is different from BA and so on. Now let's see if we can apply the factorial notation to the number of permutations when all the objects are taken. So all at a time. So we can see number of permutations is n times n minus 1 times n minus 2 times n minus 3 till 1. And you can see this is nothing but n factorial. So this is why factorial is very important in the permutation chapter, because you can see that the number of permutations for all the objects taken all together at a time, right? Number of permutations is working out to be n factorial. And we'll see another important formula where once again factorial is going to be used. Now if there are n objects and you take them r at a time, so n different objects taken r at a time. So as we discussed, how many number of permutations you have? The number of permutations was n times n minus 1 times n minus 2 all the way up to n minus r plus 1. This is what we saw earlier, right? So it's like filling up those r boxes with these n different objects. So this is what you get. Now in permutation, there's a notation for this. So when you have n different objects taken r at a time, we denote these permutations as NPR. See, we write n on top here and r below, and P stands for permutation. So this is denoted by NPR. But rather than writing this lengthy formula, we can actually simplify it. Because what did we get here? We got NPR is equal to n times n minus 1 times n minus 2 all the way up to n minus r plus 1. So let's say if I want to simplify this, what we can do here, let's say we continue this product, right? So it is n minus r plus 1, the next term will be n minus r, then n minus r minus 1, and so on all the way up to 1. Now since I added these extra terms, so I changed the formula, I can't do that, so I must divide with the same thing as well. So I must write this also as divided by n minus r times n minus r minus 1 all the way up to 1. So see, these same terms I've multiplied and divided by, so they sort of cancel out. Now if you look carefully guys, what is the numerator here? N times n minus 1 times n minus 2 all the way up to 1. This is nothing but n factorial. The numerator is nothing but n factorial. And what is the denominator? N minus r times n minus r minus 1 times n minus r minus 2 and so on all the way up to 1. So this is nothing but n minus r factorial, right? So what is our NPR formula? For n different objects taken r at a time, see, we have simplified the formula into this simple thing. So basically our formula finally works out to be NPR is basically equal to n factorial divided by n minus r factorial, where this r can be from greater than 0. So you select 1 all the way up to n objects. So where you're taking 1 or more objects all the way up to n. And this is your important formula. This is called the permutation formula for NPR. Okay. Now let's say if you take all n objects, see I've written equal to here. So if I take all n objects, will this formula work? The answer is yes. You can try it out. So you can see I've written r greater than equal to 0 and less than equal to n. So this formula will even work if you take all the objects at a time, as we'll look at in the next slide. So as we saw, our permutation formula is NPR equal to n factorial divided by n minus r factorial, where r, the number of objects that you take, can go from 0 to less than equal to n. So see, note here, r can also be n. That means this formula works for the case where you take all the n objects at a time. So let's check that if it is mathematically working. So NPR will then become NPN, where you're taking all the n objects, right? So r is equal to n over here. So it is denoted as NPN. So now if we substitute here, what do we get? N factorial divided by r I'm going to put as n. So this is going to be n minus n factorial, and n minus n is 0. So I'm getting n factorial divided by 0 factorial. And guys, like we had discussed before, remember, 0 factorial is 1. So don't forget that 0 factorial is 1. So basically we are getting n factorial divided by 1. So the answer is n factorial. And this is exactly what we expected, right? When you take all the objects at a time, again, repetitions are not allowed, the number of permutations equal to n factorial. So our formula, NPR formula, is working when r is equal to n, meaning you're taking all the objects at a time. Now usually we don't use it for r equal to 0. But what if I try it out and say NP0? What will it work out to be? Again, let's substitute r equal to 0 into this formula. So we get n factorial divided by n minus 0 factorial. So what is that? So that's going to be n factorial divided by n minus 0 is n divided by n factorial. N factorial by n factorial will cancel. So we'll get 1. So see, NP0 is giving us 1. But what does this 1 mean? So if you understand this formula, we are saying we have n objects. So let's say you have n letters. So for example, you have 5 letters A, B, C, D and E. And I tell you to select 0 objects. That means none of these letters. So how many permutations are possible? If you're not selecting any of the objects, that means you basically have nothing. So we can say that is sort of like a permutation where there is nothing, right? It's empty. So that is why you can consider that, hey, NP0 is equal to 1. That means basically nothing is taken or nothing is selected. And so that's only one possibility, because you cannot have permutations with nothing, right? So this is the meaning of NP0, and its value is equal to 1. Now let's consider the case of permutations where repetitions are allowed. So let's say you have n different objects, okay, taken r at a time, where repetitions are allowed. So you can repeat the objects over here. Then how many possible arrangements or how many permutations will there be? So once again, we'll use our box method here. So let's say you have r boxes to fill, right? You're taking r at a time. So the number of boxes we have to fill is going to be r. So 1, 2, 3, 4, and so on, all the way up to r. And we have been given n different things. Okay. So in the first box, how many things can I put? That's right, we can put n such things. In the second box, how many things can we put? See, now repetitions are allowed, so it's no longer n minus 1, because repetitions are allowed. You can again put n things. Like for example, you can consider the case of repeated letters. So suppose here you can put ABC. In the next one also you can put ABC, right? Or in the next one also you can put ABC, because repetitions are allowed. So in the third case again n. Again in the fourth box n such possibilities, and all the way for all the boxes n are allowed. So total how many permutations? Remember, we need to multiply. So n times n times n. And how many times are you doing the multiplication, guys? You're multiplying it r number of times. So finally, what is the formula? N times the n. This you're doing r times. So the formula is going to be n to the power r. So see, number of permutations when repetitions are allowed is going to be n, your number of different objects taken r at a time. So to the power r. So this is the formula for repetitions allowed, n to the power r. Now let's look at a very interesting case where the objects are not distinct. That means all the objects are not different. So let's understand this case with a simple example. Let's say you take the word root, and I ask you how many permutations can you make with the letters of the word root. So now since we have this new case where objects are not distinct, first let's assume that these are all different letters. So for that, I'm going to write this first O as O1 and we'll call this as O2. So imagine you made some changes here and these four letters are different. So with our changed word, what will be the number of permutations possible? That's right, it's going to be 4 factorial, right? You're using all the letters, or you can think it as 4p4, which is 4 factorial. So with all these distinct different letters, it would have been 4 factorial, right? 4 times 3 times 2 times 1. But now since you have two letters which are identical, we need to reduce the number of permutations. That means we need to do some division over here, right? Because we are over counting over here. Now if you have two letters, this O1 and O2, total how many permutations can you have of these? Because what we are trying to say is that when we are taking them different, O1, O2 and O2, O1 are different, right? The order matters in permutations. But finally we are saying, hey, these are actually the same thing. We have just done this cheating trick over here. So we want to see how many such permutations we have taken extra. So these permutations are going to be, since they're two letters, it's going to be 2 factorial, right? Number of possible arrangements for two letters is 2 times 1, 2 factorial. So basically, I need to divide my answer 4 factorial with 2 factorial. It's going to be 4 factorial for the 4 letters divided by, since you have this kind of repeated letter, so O1 and O2 are actually the same letter. So we are going to divide by those permutations. So the final answer is going to be 4 times 3 times 2 times 1, right? And this is 2 times 1, which is 2. So 2 and 2 will cancel. So the answer is 12. So this is a very interesting case where you have taken where all the objects or all the letters here are not distinct. So now let's generalize this. So if I ask you that what is the number of permutations when you have n objects where p such objects are of the same kind and the rest are all different, and we are doing permutations of these objects. So total how many permutations will you get? That's right, the number of permutations will be n factorial, the total possible permutations, divided by how many repetitions we have? P objects are repeated, like here 2 were repeated, 2 O's were there. So I need to divide by p factorial. Very, very important formula, right? So you guys understood that since you have these extra permutations, we are dividing by them. N factorial by p factorial is the total number of permutations here. Now let's look at another interesting case, because this whole chapter is about these interesting cases and examples. So if I give you this word Allahabad and I ask you how many total permutations can there be of these letters? So what is interesting about this word? You can see that the letter A has been repeated 4 times and the word L has been repeated 2 times. H, B and D are different, only once, right? So if it was not this special word, let's say all the letters were different, then the answer would have been very easy. Then the answer would have been simple. It would have been the number of letters here and the factorial of that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. You can see it has 9 letters. So the answer would have been simply 9 factorial. So the answer would have simply been 9 factorial had all the letters been different. Or you can think it as 9p9, because basically the number of arrangements is going to be the n factorial here, 9 factorial. But since we have these letters repeated, A has been repeated 4 times. So if you consider them as A1, A2, A3, A4, how many extra permutations are you counting? 4 factorial of them, right? There are 4 A's. So I need to divide by 4 factorial, because these A's will have 4 factorial combinations of them, which you have considered extra. And once again, for the letter, there are 2 L's. So they will have 2 factorial extra permutations over there, right? So the total number of permutations is going to be 9 factorial, the number of letters, divided by 4 factorial times 2 factorial, where 4 factorial here, so let me write it in pink color because it was representing the A here. So that is your 4 factorial, and the 2 factorial I'm going to write it in blue color because you have 2 L's over there. So if you have repetitions like this, you need to divide by each of those repetitions and taking the factorial of that, right? So let's generalize all of this. So let's say we have to find the number of permutations of n objects, where p1 objects are of the same kind, that means they are repeated. p2 objects are also of the second kind, then pk objects are of the kth kind, and so on. So what will be the number of permutations? And the rest are all different, okay? So everything is not repeated here. So then the number of permutations will be n factorial, because we always start with the assumption that, hey, everyone is different. But now we start dividing by the repetitions, right? So since you have p1 objects which are repeated, so I'll do p1 factorial. Then I have p2 objects repeated, p2 factorial, and so on till we go to pk factorial. So see, note this important formula, and you can see that that's how we did in Allahabad, right? N factorial, 9 factorial divided by, there were 4 A's, so 4 factorial, or you can say P1 factorial. There were 2 L's, so by 2 factorial or P2 factorial, and so on. If there are more repetitions, if there were, like let's say there were 3 D's, then you would have done divided by 3 factorial or pk factorial. Clear? So very, very important formula. Please note these down and you can easily apply them when these kind of special cases arise. So we have done lots of different cases and lots of different formulas. So to make it easy, let me summarize it for you. And I want you to pick up your pen and paper and write down this full summary sheet. Okay. So what did we talk about? That permutations of n different objects taken R at a time. Remember, when repetitions are not allowed, so no repetitions allowed, then it is denoted as NPR. This is that famous permutation notation or formula. NPR is basically n factorial divided by n minus r factorial. And this formula we saw, it works for r from 0 to n. Of course, r equal to 0 is the special case where you basically have no arrangement, so it works out to be 1. So this is the formula, right? And r can be n also. So if you consider taking all the n objects, then it will become npn, and we saw that is equal to n factorial. Okay, so you have that special case also, which we talked about, npn, when you're taking all the objects, but repetitions are not allowed. Now let's say we relax it and we say, hey, you can repeat, repetitions are allowed. Then the number of permutations become even more, because you can fill all those R boxes with n things, right? Each time you can put any of the n things, right? So the number of permutations become simply n to the power r, because remember, you're filling up R boxes each with n things. So n times n times n times n, r times, so it is n to the power r. All right. Then we looked at these special cases where you're talking about doing permutations of n objects where p objects are exactly of the same kind. Like we saw that repeated letter O, right? O was repeated 2 times. So then the number of permutations, the formula becomes n factorial, as if all of them were distinct, but you're dividing by that repeat by p factorial. So n factorial by p factorial. Clear? And then we can extend this formula to the case where you're doing permutation of n objects, where p1 of objects are of the same kind, p2 objects are of another kind, of the same kind, pk are of the same kind. So the final formula becomes n factorial divided by p1 factorial times p2 factorial and all the way up to pk factorial. So basically we are generalizing this formula. So very, very important, please write these down, and when you're doing questions, you'll have to consider that which case are we doing. Or sometimes you have to think logically, draw the boxes, but you must understand these formulas. Again, we will always try to apply the box method, because there you're visualizing the thing, but knowing these formulas is very useful because it helps you solve the questions really fast. Okay, so make sure you write this down and learn these formulas. So now let's try some questions on permutations. Here's the first question. How many 3-digit numbers can be formed by using the digits 1 to 9 if no digit is repeated? So once again, you can visualize it with the box method, or maybe you can use the formula method. First, let's visualize this question with our box method. So since we have 3 digits, I'm going to represent it as 3 boxes, where the first box is the unit digit, then the tens digit and the hundreds digit. And here it's saying that we want to form these digits, redoing the last dialog, and here it's saying that we want to form these 3-digit numbers using the digits 1 to 9, but the digit repetition is not allowed. So if you're filling in these 3 digits, these 3 boxes, what are your options? So if we start with the hundreds digit, so let's say you can put any of these 9 digits, 1 to 9. So you have 9 possibilities here. For the tens digit, since you have used up 1, you have 8 possibilities left. And now since you've used up 1 more, 7 possibilities. So do you guys agree, since no digit is repeated, how many possible permutations are there? 9 times 8 times 7. And if you multiply this out, you'll see the answer is 504. 504 such 3-digit numbers are possible with no digit repeated. So this was our box technique where we analyzed it and found the answer. You can also do this by formula method, because remember, we learned this formula NPR, where you have n different objects taken r at a time. So what are our objects here? The objects are the digits 1 to 9. So how many such objects? That's right, n is equal to 9 here. So we are talking about, if we use the NPR formula, which remember it was n factorial by n minus r factorial. In our case, n is equal to 9 for the 9 digits. And how many digits are we using? We want to form 3-digit numbers where repetitions are not allowed. So we are taking only 3 digits at a time. So do you guys agree that r equals 3? So basically the answer will be 9p3, which is equal to 9 factorial divided by 9 minus 3 factorial. So that's 9 factorial by 6 factorial. So what will the final answer be? 9 factorial is 9 times 8 times 7 times 6 factorial divided by 6 factorial. So see, the 6 factorial will cancel out. So our final answer is 9 times 8 times 7, which is 504. So see, 504 such numbers are possible. And with the formula method, because it is equal to 9p3. So whichever way you want to use, but I always recommend first visualizing the question with the box method, because sometimes, you know, with formulas, you can get too much entangled into the formulas. So you can directly do this, right? 9 times 8 times 7. Or if you find it easier in these questions to think in the formula method, that's absolutely fine. But just make sure that you're using the right formula. So here it was NPR. And as you can see, the answer is the same. Now let's try another question. You have to find how many 4-digit numbers are there where no digits are repeated. So once again, let's visualize it with our box technique. So we'll draw 4 boxes to represent 4-digit numbers. So these are the 4 boxes here. There you go. This is the thousands digit, the hundreds digit, the tens digit, and the units digit. Okay. So that's representing a 4-digit number. Now we need to fill in these with the digits. And what are the digits? Digits are from 0 to 9. So 0, 1, 2, 3, all the way up to 9. So how many digits do you have at your disposal? You have 10 digits. But we need to make sure no digit is repeated. So let's start filling our boxes, because this box method is very powerful. It helps us visualize. So in the first place, in the thousands digit, how many digits can I put? Can I put all 10? The answer is no, because you cannot put 0. Suppose you put 0 here and let's say your number is 0, 2, 3, 4. This is no longer a 4-digit number. It is actually a 3-digit number, because 0 in the thousandth place makes no sense. This is a 3-digit number. So we can have only 9 possible numbers here from 1 to 9. Right? Now moving on to the hundreds place, since we have used up 1 digit and repetitions are not allowed, how many digits are left? So 10 minus 1, 9, right? So we can put any of the 9 digits here, and this time 0 is allowed, because you can have a number such as 2034. See, this is a 4-digit number where 0 is in the hundreds place, right? So here it's 9 times 9. Now once again, since a digit cannot be repeated, how many digits are left? 9 minus 1, 8. So in the tens place, we can put 8 digits. In the units place, we can put 7 digits. So what are the total number of permutations possible? So the total number of permutations possible here are, or the number of 4-digit numbers possible is 9 times 9 times 8 times 7. And if you multiply all that, you will be getting the answer as 4,536. This is our final answer here. And can you see, for these kind of questions, it is more difficult to think in terms of formulas. The box method is easier, more powerful. So I highly recommend that you first visualize the question and try to think with the box method and use the formulas only if needed, right? Where it helps you to quickly think in terms of NPR, or, you know, when you have those repetition of objects, then formula works fine. But here you had to actually analyze and see what digits are possible. So definitely this box method, this analysis method is much better, and it will help you work out the answer easily here. Now let's try an interesting question based on this permutation notation. So we have been given find n if n minus 1 p3 is 2. So we are taking the ratio np4 is 1:9. So let's write this down clearly. So what do we have? N minus 1 p3. So you're taking these permutations divided by np4 equals 1/9. So remember, this is using that NPR notation. What was NPR? NPR was n factorial divided by n minus r factorial, where basically you have n different objects taken r at a time. So let's plug in the values here. So on the left hand side, what do we have? This is going to be n minus 1 factorial divided by n minus r factorial. So n minus 1 minus 3 factorial. So this is nothing but n minus 4 factorial. So I'll just erase and write the denominator as n minus, it's not r, it's 4 factorial here. Okay. And then you have divided by, so I'll just write the divided sign since we have these fractions over here. And what is np4? It is n factorial divided by n minus 4 factorial. And this is equal to 1/9, right? So let's go ahead and simplify this stuff. So what have we got? N minus 1 factorial by n minus 4 factorial. And so this division we can change it into a multiplication by taking a reciprocal here. So this is going to become n minus 4 factorial divided by n factorial, and that's equal to 1 by 9. So the main thing is you should never expand out. You should see if things will cancel to simplify things here, and you can see that n minus 4 factorial is nicely cancelling out over here. Okay. Now let's see what we can simplify here. So we have n minus 1 factorial by n factorial. So we know that the denominator is nothing but n factorial is nothing but n times n minus 1 factorial, and on the right hand side we have a 1 by 9. So see, once again we can cancel the n minus 1 factorial here. So what are we left with? We are left with 1 by 9, 1 by n equal to 1 by 9. So the answer is so simple, n is simply equal to 9. So there you go, the answer is so simple, n equal to 9. And the main trick is use this formula that we have learned, NPR formula, apply it here, simplify the stuff, and you will easily get your answer. Now let's try out this question. Once again, you can see we have the NPR kind of notation here. So we need to find R if 5PR equals 2. So this is multiplied by 2 times 6PR minus 1. So let's use our formula. What is the NPR formula? NPR is n factorial divided by n minus r factorial. So let's go ahead and use this formula here. So 5PR is nothing but 5 factorial divided by 5 minus r factorial. This is the left hand side, right? N minus r factorial. And here you have 2 times, this is going to be your n is 6. So 6 factorial divided by 6 minus r minus of minus 1. So that becomes plus 1 here, factorial. So now go ahead and simplify this. So what do we get on the left hand side? We have 5 factorial divided by 5 minus r factorial. And on the right hand side we have 2 times 6 factorial divided by, this will give you 6 plus 1 is 7 minus r factorial. Now go ahead and see what you can simplify here, because once again don't multiply out stuff. So remember, we can use that trick of expressing the factorial in terms of the previous number. So we can say on the right hand side, I can express 6 factorial as 6 times 5 factorial. Okay. Here we have 5 factorial in the numerator, and this is 5 minus r factorial. In the denominator here, we can write 7 minus r factorial as 7 minus r times 6 minus r times 5 minus r factorial. See, we can keep going down. So now you can see things are cancelling out. So the good news is 5 factorial cancels. 5 minus r factorial gets cancelled. So see, things are simplifying out. So what do we get over here? So finally, if you multiply, if I take this to the left hand side, 7 minus r and 6 minus r equal to 6 times 2, which is 12. So let's go ahead and simplify the left hand side. So what will we get over here? 7 minus r times 6 minus r, if you expand out, you'll get 42 minus, so you have a 6r and a 7r, so that's going to give you minus 13r plus r square equal to 12. So see, we are getting a quadratic equation. So let's solve this quadratic equation, guys. So if we solve it, what are we getting? R square minus 13r, so simplifying it, plus, what do I have here? Plus 30 equal to 0. So this is our quadratic equation. We can do middle term breaking. So 30 I can split as 3 times 10, and so we'll be using minus 3 and minus 10 because we need minus 13r. So using middle term breaking here, r square minus 3r minus 10r plus 30 equal to 0. So if we take r in common, r minus 3 minus 10 times r minus 3 equal to 0. So taking r minus 3 common, we are getting this as our quadratic equation. So what is the solution? Either r is equal to 3 or r is equal to 10. Are both these answers possible? Look at what is given to us. So if you put r as 3 or 10, will it be possible? Will 5p10 make sense? No, because remember in the NPR formula, r can take on values from 0 to n. 0 is the special case, so You can take it as a equal to or greater than over there, whatever is given in your books, because 0 means you're taking nothing. But here basically r should be less than equal to n. It cannot be greater than equal to n. And here you can see we have 5 over here, we have 6 over here. So definitely this one is not possible. The 10 solution is not possible. So we have only one answer possible, r equal to 3. If you write both possibilities, 3 and 10, you will get a cross because your r cannot be greater than n. So this is our final answer, r equal to 3 here. The next question is dedicated to all the daughters. So let's take a look. Find the number of different 8-letter arrangements that can be made from the letters of the word daughter. So this is the word given to us so that all the vowels occur together. So what are the vowels here? So if you look at the word daughter, you can see the vowels are A, U and E over here. So this means we want to find all the possible arrangements, but we want the vowels together like one unit. So let me separate the consonant and the vowel. So I'll have D, G, H, T, R, these 5 consonants, and the vowels are A, U and E. Now the vowels can come anywhere, so we consider them like as one unit. So I'm going to call this one unit as V. So it's like we have these letters now, V, D, H, D, G, H, T, R. So how many total permutations are possible? Because the vowels should occur together. They should not be separated. So how many total permutations, guys? So if you look at it, there are 1, 2, 3, 4, 5 letters and we are considering this vowel as one object. So 6 objects over here. So total number of permutations, so I'm going to write number of permutations is going to be 6 factorial, or you can think 6p6, right? 6 factorial permutations are possible. But these vowels also could be arranged in any order, A, U, E, A, E, U and so on. So how many permutations of the vowels are possible? There are 3 vowels. So 3 factorial permutations, right? So these vowels can be permuted in 3 factorial ways. So the total number of permutations is going to be 6 factorial multiplied by this 3 factorial. Are you guys getting it? So the final answer is going to be, the total number of permutations possible is 6 factorial multiplied by 3 factorial. And you guys can multiply this out and work it out, but many times in your school, they are fine if you leave this as the answer in terms of factorial notation. So this is the total number of permutations possible where all the vowels occur together as one unit. Now let's look at part 2, because this was part 1 here. Part 2 is asking how many permutations where all the vowels do not occur together. So we do not want this, where all the vowels are, packed up together. So this is very easy, because what we can do is we can find all the permutations of the word daughter, right? All the permutations of the letters, and then subtract all these where they occur. So here part 2 should be pretty simple, because we'll say the number of permutations here is going to be the total number of permutations minus what we just found where they occur together, which was 6 factorial times 3 factorial. Now what is the total number of permutations possible? Wow, the word daughter has 1, 2, 3, 4, 5, 6, 7, 8 letters here, right? So this is going to be 8 factorial total permutations minus 6 factorial times 3 factorial. Now again you have a big number here, but you can simplify it. So if you write 8 factorial as 8 times 7 times 6 factorial minus 6 factorial times 3 factorial. So see, I can take this 6 factorial out in common. So I'll have left 8 times 7 minus 3 factorial, which is 3 times 2 times 1, which is 6. Now 8 times 7 is 56. So 56 minus 6 is 50. So we are left with 6 factorial times 50. And if you calculate what is 6 factorial? 6 factorial will work out to be 6 factorial is basically 6 times 5 factorial, and 5 factorial, if I remember, is 120. So 6 times 120 times 50. So if you guys multiply out the numbers, you will get the answer as 36,000 over here. This is the final answer for the part 2. So the whole concept was that you find the total permutations and subtract out the ones from part 1, and this is how you can solve this interesting question. So here's the important summary of all the permutation formulas that we did. So make sure you guys note this down. This will really help you and you can use these formulas in the questions. So note down this important summary of all the formulas that I've given here. And now here's an interesting homework question for you guys. So the question is, how many numbers lying between 100 and 1000 can be formed with the digits 0, 1, 2, 3, 4 if the repetitions of digits is not allowed? So go ahead and try out this homework question and use the concepts that you have learned, and do let me know your answers by putting it in the comments below. So I'm looking forward to reading your answers. So try this homework question and put your answers in the comments below. Friends, I hope the concept of permutations is crystal clear to you now. So go ahead and apply the techniques that you've learned in this video, and I'm sure you'll be able to solve the questions on this permutations topic. And do remember to like this video and share it out with your friends. And if you haven't subscribed to our YouTube channel, guys, what are you waiting for? Smash that subscribe button right now and click on the notification bell so that you don't miss out on any of our videos. And do check out the courses on our website manochaacademy.com and our Android app Manocha Academy. We have courses on physics, chemistry, biology, mathematics, coding, and artificial intelligence. In these courses, you're going to get live classes, interactive videos, quizzes, questions, mock tests, and revision notes. So guys, what are you waiting for? Do check out the links given below and please do share it with your friends. So stay connected with us and just keep learning.